Hey everyone! Today we're going to talk about a piece of technology that is, I'm not kidding, absolutely everywhere. It's working silently, right now, to power our world, cool our homes, and even get us to work. It's this sort of invisible climate controller, and I promise, once you know what it is, you're going to start seeing it everywhere. So let's pull back the curtain on this amazing hidden tech.
So, let's start with a little riddle. What do a car radiator, an air conditioner, and a gigantic power plant all have in common? I mean, they seem totally unrelated, right? One keeps your engine from exploding, one keeps you from melting in the summer, and the other powers entire cities. But they all share one single critical piece of engineering at their very core. Any ideas?
You got it. It's the heat exchanger. This is the unsung hero we're diving into today. This is the device that makes it all happen. Your car, your AC, our power grid, all by being a master of moving heat from one place to another. Okay, so what is it really? Simply put, a heat exchanger is just a device that moves heat energy from one fluid, that could be a liquid or a gas, to another. But here's the magic trick, the really important part. The two fluids never, ever mix. They never touch. All of that heat transfer happens through a solid barrier, letting the energy cross over while keeping the fluids totally separate. Now, you'll find these things in all sorts of crazy shapes and sizes, but pretty much all of them are built on one of two basic designs. So let's take a peek inside and see how these things are actually put together. So on the left, you've got the workhorse, the most common type you'll ever see, the tube and shell design. And on the right, you have the plate design. Now, plate exchangers are incredibly good at what they do. They pack a huge amount of surface area into a really small space. But, the trade-off is that sealing all those tiny plates can be a real headache. That's why the simpler, tougher tube and shell design is still the king in most heavy-duty industries. All right, let's break down that tube and shell type. You've got the outer casing, that's the shell. Inside, there's a whole bundle of tubes that carry your first fluid. At the ends, a strong tube sheet holds it all together and makes sure nothing leaks. And see those little plates inside, kind of spaced out? Those are called baffles, and they are super important. They don't just hold the tube steady, they force the other fluid to take this long, winding, zigzag path across the tubes, which makes sure it picks up as much heat as possible. It's a really clever design. Okay, now we get to the really cool part. The secret sauce to how well a heat exchanger works is all about the direction the fluids are flowing. There are three main ways to do it, and believe me, the difference between them is just massive. First up, we have parallel flow. Pretty simple, right? Both the hot and the cold fluids jump in at the same end and travel in the same direction. And you can see it right there on the graph. They start with this huge temperature difference, so you get a ton of heat transfer right at the beginning. But as they move along, their temperatures get closer and closer, and the whole process just kind of fizzles out. It gets the job done, but it's definitely not the best way to do it. But now, check out counterflow. Here, the fluids enter at opposite ends and flow right past each other. This is a total game changer. Because the coldest fluid is constantly meeting hotter and hotter fluid along its path, that temperature difference, the driving force, stays pretty high the whole way through. And this lets you do something that seems impossible. The cold fluid coming out can actually get hotter than the hot fluid that's leaving. Mind-blowing, right? This is peak efficiency. And last, you've got crossflow. This is just what it sounds like. The two fluids pass over each other at a 90-degree angle. You see this design a lot in things like steam condensers, where you have this huge cloud of vapor that you need to pass over a bunch of cool tubes to turn it back into a liquid. Okay, so we've got our three contenders: parallel, counter, and cross. But which one is actually the champ? When you put them head-to-head, who wins? Well, the numbers make it pretty clear. It's not even a contest. In the exact same setup, the parallel flow design moves about 320,000 BTUs per hour. A BTU, by the way, is just the energy it takes to heat about a pound of water by 1 degree Fahrenheit. Now look at counterflow, 380,000 BTUs per hour. That's a huge jump in performance. And it's all because it keeps that average temperature difference higher across the entire device. It just works better, plain and simple. Let's just park on that number for a second. 380,000 BTUs every single hour. That is a staggering amount of energy being shuttled from one fluid to another without them ever touching. This raw power is exactly why engineers love the counterflow design for anything that needs top-tier performance. All right, enough of the theory and the charts. This stuff is way more fun when you see where these devices are actually working, hiding in plain sight. So let's go on a little scavenger hunt and find some exchangers out in the wild. Every single time you get in a car, you're using one. Your car's radiator is a perfect example of a cross-flow heat exchanger. You've got hot liquid coolant from the engine running through all these little tubes. At the same time, air is rushing across them from the outside. And all those little wavy metal fins, their job is to create a massive surface area, because air, on its own, is actually a pretty lousy conductor of heat. What about your air conditioner? Well, it actually has two of them. There's one inside your house called the evaporator. It absorbs all the heat from the air in your room. Then it pumps that heat outside to the second heat exchanger called the condenser, which dumps all that unwanted heat into the outdoor air. Your AC isn't making cold, it's just moving heat from inside to outside. And on an industrial scale? Oh yeah, they're absolutely everywhere. This monster is a feed water heater from a power plant. Think about it. Trying to take freezing cold water and turn it into superheated steam all in one go would be super inefficient and would put a ton of stress on your equipment. So instead, they use waste heat from other parts of the plant to preheat the water in stages. It saved an incredible amount of energy. And this might be one of the most important jobs of all. This is a power plant condenser. After steam blasts through a turbine to generate electricity, you've got to turn it back into water so you can use it again. This gigantic heat exchanger does that, but it also does something else. By rapidly cooling the steam, it creates a powerful vacuum, which helps pull even more steam through the turbine, squeezing every last bit of energy out of it. Now here's a cool bit of engineering jargon for you. Condensate depression. This is basically how much you overcool the water after it's already turned back from steam, and it's a real balancing act. You actually want to cool it a few extra degrees to stop dangerous vapor bubbles from forming in your pumps. But if you cool it too much, you've just wasted a bunch of energy because now you have to spend more energy to heat it back up again for the next cycle. It's tricky stuff. So, as you can see, the heat exchanger is so much more than just a simple piece of plumbing. It's a fundamental tool that lets us manage, recycle, and control energy itself. And it's doing that in almost every part of our modern lives. From your car to your house to the power plants that light up our world, these things are the invisible engines running everything. So the next time you feel that blast of cool air from an AC unit, you'll know the secret. You're in on it. Which leaves us with one last big question. Now that you know how to spot them, what's next? What future problems in energy, in computing, maybe even in space travel, could we solve if we get even better at mastering the flow of heat?